Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all. Here we are with chapter 7 of microwave engineering, where the microwave transmission lines we are addressing. So up till now into the subject we have generated the microwave energy based on to the vacuum tube platform with the principle of velocity modulation, and then onto the semiconductor platform, most possibly into the principle of negative resistance. So here we have handled the microwave energy for the amplification purpose. The oscillation is basically generating the energy, and now in this particular chapter up till now we have addressed the equivalent model with the help of certain lumped parameters for the transmission line and found the solutions with respect to the transmission line equations. So based on to the formulations that we have seen into the previous video regarding the solution to the equations of microwave transmission line, let us solve a simple problem. So here we are provided a problem statement. The problem statement is a transmission line has the following parameters. The parameters are represented as the lump parameters. Capital R is equal to twice ohm per meter. Capital G is equal to 0.5 millimho per meter. F, the frequency, is equal to 1 gigahertz. Then we have capital L is equal to 8 nano henry per meter, and C is equal to 0.23 picofarad here. We are asked to calculate in the part A the characteristic impedance and in the part B the propagation constant. So to read the problem statement, here we have the lump parameters capital R in terms of per unit length. So here the resistance R is always measured in terms of ohms. So here we have resistance per unit length in terms of ohms per meter, that has the value 2 here. Whereas we have the conductance represented by capital G, it is also per unit length. Here it is provided mho per meter, especially millimho per meter. So we have the value of conductance G to be 0.5 into 10 raised to the power minus 3 for the millimho per meter. The operating frequency, here we have 1 gigahertz, that it is 1 into 10 raised to the power 9 into hertz. Here we have the inductance is also per unit meter. The per unit length we can say that it is 8 into 10 raised to the power minus 9 we can go for the nano case, henry per meter. Whereas the capacitance is provided 0.23, we can take 10 raised to power minus 12 for the picofarad here. Now we require the calculation of characteristic impedance. The characteristic impedance for the transmission line we represent with the help of capital Z suffix 0, whereas the propagation constant that is need to be calculated into the part B is denoted by the Greek symbol gamma here. So let us have attention to make calculation for part A, the characteristic impedance. So as we have the problem statement with the given values of the resistance, the conductance, the inductance and the capacitance values. These are the lumped elements as per as the equivalent circuitry for the transmission line model we can say here we have. So we express the characteristic impedance Z0 in terms of these lumped elements, and we have the formulation that it is square root of, here we have in the numerator capital R plus j omega L, in the denominator here we have capital G added with j omega C here. So in both the numerator and the denominator under square root we have the real and the imaginary part. So L and C constitute the imaginary part, whereas the R and G constitute the real part. Now it's time to make substitution. So here by the next step, to find the characteristic impedance Z0, in the numerator in place of capital R we substitute the value provided that it is 2. So we further add it with j omega. Omega can be written as 2 pi into f, whereas the value of f, the operating frequency over the transmission line, is provided to us. The value is 1 gigahertz. Therefore, we keep the second term, that it is j into 2 pi into, here we make 1 into 10 raised to the power 9 for the gigahertz. Whereas the value of L, is provided 8 nano Henry per meter. So here we put 8 into 10 raised to the power minus 9 for the nano. So this is the numerator. Now we substitute the values to the denominator. In the denominator, we first of all encounter with the capital G, that it is 0.5 millimole per meter. So here we substitute 0.5 into 10 raised to the power minus 3 for the milli case here. Now we need to make it addition with the j omega c. So as before, we have j omega can be 2 pi f. So as like the numerator term, here we have 2 pi into 1 into 10 raised to the power 9. Now we require the value of c, that is provided to us. The value is 0.23 picofarad. Hence we write 0.23 into 10 raised to the power minus 12 here. So in this step, the substitution of all the lumped elements R, L, G and C is completed here. Now as the values are provided into the real and imaginary parts, I must say this is the complex representation of the values here. Now for the convenience of computation here, we get it converted to the polar representation here. So in the polar representation, we get the square root as it is, and for the numerator, 2 plus j times 2 pi into 1 into 10 raised to the power 9 into 8 into 10 raised to the power minus 9, where 10 raised to the power plus 9 and minus 9 will get cancelled. We have the equivalent representation into the polar form, that it is real part, it is 50.31, whereas the angle part that we have calculated, that it is 87.72 degrees here. So here this conversion from the complex representation to the polar representation can be simply performed onto the engineering calculator here. So the same procedure we opt to represent the complex representation into the denominator to the polar representation. So therefore we have the denominator under the square root, real part 15.29 into 10 raised to the power minus 4. The angle we have obtained, that it is 70.91 degrees here. So the division of the same domain and taking the square root, we obtain the next step for determination of the value of characteristic impedance. This value is 181.39. In the angle we have 8.40 degrees. So this is the value of characteristic impedance represented into the polar form, which can also be expressed into the complex domain. So we get it the reverse conversion from the polar form to that of the complex domain. Here we obtained the real part 179.44, and we add it with the imaginary part representing the j, the imaginary factor. So here we have 26.50. So this is the value of characteristic impedance represented both in polar and complex domain here. So this completes the answer for part A. So here we get back to the problem statement. In the problem statement, we were asked to calculate two parts A and B. So the answer for part A is calculated here. Now we require to make calculations for the propagation constant gamma, provided the values of lumped components R, G, L, C along with the operating frequency value here. Now for determination of the propagation constant, we have the representation for part B to be the gamma propagation constant expressed in terms of the lumped parameters The formulation is taking the square root. Inside here we have the first bracket that involves r added with j omega l, and the bracket is completed which has the multiplication to another bracket that has capital G added with j omega c here. So from the earlier part A, we have r plus j omega l and g plus j omega c computed into the polar form. So here we take the square root. For the first bracket, we represent within the parenthesis 50.30, the real part, along with the angular portion 87.72 in terms of degrees here. So this is the first bracket represented into the polar form after substitution of r and l along with omega replaced by 2 pi f. The value of f is 1 gigahertz here. So in the polar form here we have, this is in multiplication to the substitutions to the g and c as like the case we have done in the previous portion, and getting it converted we have 15.29 into 10 raised to the power minus 4. The angle is 70.91 degrees here. So the substitution is made and the multiplication here inside the square root, giving us the next step for the propagation constant gamma equal to, here we have the square root of the 769.24 into 10 raised to the power minus 4 will be the real part, whereas the angular part is 158.63 into the degrees here. Now if you take the square root for determination of gamma, we obtain the real part 0.2774, whereas the angle part is 79.30 degrees here. Now when we get it converted to the complex representation, real and imaginary part, we obtain the real part as 0.051. So it is added with the imaginary part plus j times 0.273. So this is the required answer for gamma. So in this representation, gamma is nothing but the propagation constant for the given transmission line here. So here we get back to the problem statement. For the given transmission line with the lumped elements per unit length of that particular transmission line along with the operating frequency, we are now successful to determine the characteristic impedance and that of the propagation constant. By the next lecture, we continue with the same chapter, microwave transmission line, to see the details of the reflection coefficient. I hope you enjoy learning the microwave engineering subject. For the more details of the concepts related to these chapters of microwave engineering along with the practice of several problems, you can subscribe to Ekeeda channel. Thank you.